Today we're going to talk about acids and bases and their characteristics and nomenclature. Now, nomenclature simply means, remember, how we name and write formulas for these acids and bases. We did a lab, and that lab helped us to see some of the different characteristics of acids and bases. Now, we didn't actually taste anything in lab, but one of the things that's true about acids is that they tend to taste sour. We've seen that happen. We mentioned in the lab that it happens with our citric acid containing fruits like lemons and limes and oranges and grapefruits. So that's an example of an organic acid and how it tastes sour. Acids react with metals to produce hydrogen gas. We saw that occurring in the lab. Acids also react with carbonates to produce carbon dioxide in chemical reactions. Geologists use this type of reaction to find different types of rocks and minerals. Acids also affect indicators. We saw this happening. The two main ones that we should be familiar with at this level are litmus and phenolphthalein. Blue litmus will turn red if there's an acidic solution, whereas if we have phenolphthalein in an acidic solution, it's going to be clear. And we'll look in a moment at how that changes when you have a basic solution. Acids have pH values less than 7. We'll get into that more when we talk about pH and pOH later in our notes on another day. Acids can cause severe burns. We'll also be mentioning the fact that and talking about the type of reactions and showing the type of reactions that indicate that acids will react to produce hydrogen ions. They will ionize in water in order to produce those hydrogen ions. And guys, this is what makes an acid be an acid. If we don't have hydrogen ions in the solution, then we don't have an acidic solution. So when you think when you think acid, you should immediately think hydrogen ions. They are a pair. Acids in general, the ones that we'll be studying primarily this year, begin with an H, things like HCl, H2SO4, HNO3, etc. We'll see one major exception to that here in just a little bit when we look at some nomenclature. Now, I just put the definition of indicator down here. When we talk about litmus and phenolphthalein, those are substances that change color in acidic versus basic solutions. And we can use those indicators to show or to differentiate between those two types of solutions. Now, bases taste bitter. Again, we're not going to taste anything in the lab, but if you've ever had some of the soaps in your mouth, they're very bitter. They feel slippery. They also affect indicators, and notice that in the case of bases turn red litmus to blue, and if they are in phenolphthalein, they are a magenta or hot pink color in basic solutions. Those indicators have definite color changes depending on acidic or basic solutions that they're in. Bases have pH values greater than 7. They can cause severe burns just like acids can. We always see these horror movies where acids are eating people's skin away and stuff like that. Well, bases can cause severe burns as well. And acids don't really work quite that way, especially the ones we'll be using in class. Yes, even if you pour concentrated acid on your skin, if you rinse it off quickly, it's going to probably not even leave a mark of any kind. Bases can burn you as well. Now, eyes are a totally different situation. So obviously when we're dealing with acids and bases, we are going to be very, very diligent about wearing goggles. Bases react to produce hydroxide ions, whereas when you think of an acid, you should think of hydrogen ions. When you think of a base, you should think of hydroxide ions. If it doesn't have hydroxide ions in it, it is not a base. So the big characteristic for bases. They have formulas which in general end with OH, NaOH, BaOH2, etc. So those are some indications that you're dealing with a base. Salts, then, another type of compound, are ionic compounds. These are substances, and ionic compounds, of course, we've studied for most of the year. have a metal or an H4 plus, a polyatomic ion, at the beginning, plus a nonmetal. Those are our ionic compounds or our salts. Naming bases is something we've done. We haven't called them bases in the past, but they're named just like we've always named substances. In the case of this first one, sodium, since sodium is in group 1A, it does not need a Roman numeral. Remember, if it's in groups 1A or 2A, it does not need a Roman numeral. Neither do our always true. Silver, cadmium, zinc, aluminum. Those are our always trues. They do not need Roman numerals either. So sodium hydroxide for this one. And if you look at where barium is, barium's in group 2A, and since it's in group 2A, barium does not need a Roman numeral either. So all we have to write for this one is simply barium hydroxide. Don't put prefixes on ionic compounds. This is not barium dihydroxide. We do not use prefixes on ionic compounds, only on molecular or covalent compounds. So the next one, however, iron, Fe, is a transition element, and transition elements, transition metals, do need Roman numerals unless they're one of the always truths, and iron is no exception. Now, the beauty part of hydroxides is that since hydroxides are -1 charged polyatomic ions, all we need to be able to look at in order to determine what the Roman numeral is this N number right here. This N number is a 3, and that's going to tell us that we need iron to have a charge of 3 in order to balance out those 3 hydroxides. So just by looking at that N number, we'll be able to tell what the Roman numeral is. So iron 3 hydroxide. There then is one base that I expect you to know, and we'll learn in the next set of notes why this acts as a base when you put it in water. But for now, just realize it's a weird base. I know that. It does not have hydroxide in it, but it is a base. This is ammonia, and I expect you to memorize this one. It's an exception to the rule. So now let's look at naming acids. If we're naming a binary acid is an acid that contains only 2 elements, hence the term binary. If it's a binary acid, it always begins with hydro. So this is the rule right here. Kind of got squished together a little bit on these notes, but hydro plus the root of the element that is in there that's other than hydrogen, plus ic on the end. So for instance, for HF, this would be hydro. It only has 2 elements, and one of them is hydrogen, so hydro starts it. Since it's fluorine, we're going to use the root, which is just the fluor part, and it's going to end in ic and acid at the end. So hydrofluoric acid. And you can pause this for a minute and see if you can name the last 2, HCl and H2S, based on this rule. So hopefully when you did this, you came up with the fact that HCl should be hydro, the root for chlorine, which is chlor, ic, acid, hydrochloric acid, and H2S, hydro. Now this one sometimes causes people a little bit of trouble, but sulfur doesn't really use the root. Sulfur and carbon, both of those use the entire name. So this is going to be hydrosulfuric acid. Hydrosulfuric acid. So that's how you name binary acids. If, on the other hand, the acid has more than 2 elements in it, it's got hydrogen plus another element plus oxygen, then you're dealing with an oxyacid, sometimes called a tertiary acid. There are some definite rules that most of these tertiary acids or oxyacids follow, and the ones that follow the rule are the halogens, carbon, and nitrogen oxyacids. If there's one oxygen, it's all about how many oxygens there are. If there's one oxygen, then we start with hypo for the prefix, we use the root, we end it with us, and we tack acid on the end. If it's got two oxygens in it, we have no prefix, we just have the root and end it with OUS and tack acid on the end. Three oxygens, no prefix, just the root and ic on the end with acid tacked on. And finally, if it has four oxygens, we go back to a prefix per, we put the root, ic, and an acid. This is a set of rules that you're going to have to memorize, so you might as well, as you're writing these, try to internalize this information so that when you take the test over this, you'll be able to remember the rules for the number of oxygens. So HFO, and I actually meant for this, I notice it now that it's a mistake. There should be a 2 here. I want to show an example of all of them. So please change that in your notes if it hasn't already been changed. HFO, we notice that HFO has one oxygen, so we're going to use this first rule up here. So we're going to start it with hypo, the root fluor, F-L-U-O-R, and it's going to end with us, it said, O-U-S, hypofluorous acid. Now, I really think after seeing this that you could go through with the rest of these and name them using the rules. So why don't you pause it for a minute and see if you can name the next 3 examples using these rules. So hopefully you did this, and for HBrO4, you notice that there were 4 oxygens, so it's going to be named according to this last rule. We're going to start it with per. Bromine has the root brom, B-R-O-M, and it's going to, it says in the rules, end with ic, per bromic, and of course acid tacked on the end. HNO2 has 2 oxygens. Since it has 2 oxygens, we're going to use the second rule for 2 oxygens up here. It doesn't have a prefix, it simply starts with the root, nitro, or nitra, and it's going to end with OUS, so nitrous acid. Finally, the last one with 3 oxygens. The 3 oxygens, we're going to use the third rule for 3 oxygens, of course, and it's not going to have a prefix again. It's simply going to start out with carbon. It doesn't have, remember I told you earlier that carbon did not shorten its name. It used the entire name just like sulfur does. So carbonic acid. So that's naming the ones that are named according to the rules. The sulfur and phosphorus acids. Sulfur and phosphorus acids do not follow the rules. So if you see a sulfur or a phosphorus acid, you'll need to come back to this set of notes and look to see that it's actually like 1 oxygen off. H2SO3 is sulfurous acid. H2SO4 is sulfuric acid. Same thing with H3PO3, phosphorus acid, and H3PO4, phosphoric acid. Notice also that there are different numbers of hydrogens. We saw it first up here with the carbonate polyatomic ion. Remember, carbonate's a 2 negative, which is why it needs 2 hydrogens. Both sulfite and sulfate are 2 negative ions, which is why they need 2 hydrogens. Phosphite and phosphate are our only 3 negative ions, which is why they need 3 hydrogens. So we have to keep that in mind. And finally, the last one is an exception to the rule. It is an organic acid. There are lots and lots of organic acids, but this one is the one that I'm going to ask you to memorize, to remember. There's another formula that's often used in inorganic chemistry, and it looks more like the acetate I had you memorize at the beginning of the year. Remember CHO 232? Both of these are the same formula for acetic acid. Now, a lot of people say acidic acid. It's not acidic acid, it's acetic acid. It is the main ingredient in vinegar. It's what gives vinegar its characteristic smell. So that is a very common acid in AP, and just like ammonia is a very common base in AP, which is why I'm asking you to memorize those at this level. So the last thing we want to do is to be able to write formulas for these acids and bases. As soon as we see hydro at the front, remember, hydro at the front, if you look at the top of the notes on this page, tells you it's a binary acid. And a binary acid simply has H at the front with the root, the element for the root, which is brom, which is bromine, and it's HBr. Perchloric acid, as soon as it starts with a per, we know that it has an H at the beginning and 4 oxygens at the end. Look at the rules up above. If it starts with the prefix per, it's for the 4 oxygens. And since chlor is the root word for chlorine, the middle element's going to be Cl. Pause it real quick and see if you can write the formula for fluoric acid. Okay, hopefully you realize that fluoric acid, since it did not have a prefix and it ended in ic, was a 3-oxygen acid. So this would start with H and end with O3. And since fluor is the root for fluorine, HFO3. Phosphoric acid, there's no way to do this but to remember that phosphorus acids and sulfur acids are exceptions to the rule. Bells should go off in your head if you see either one of those at the beginning of an acid name, and look on our rules right above on this page. You'll see that phosphoric acid is H3PO4. Aluminum hydroxide, we know it's aluminum and hydroxide. We'll need to know charges. Aluminum is a +3, hydroxide is a -1, so that tells us we're going to need 3 hydroxides to be to balance out 1 aluminum. Hypobromous, when it starts with hypo, look at your rules above. Hypo at the beginning, us at the end, tells us that this is an acid that starts with H and ends with 1 oxygen. Brom is the root for bromine, so HBRO. Iodous acid, sometimes the iodine acids kind of throw us for a loop when we see them in formulas. Watch for those. There is no prefix and it ends with us. That tells us that we are going to be starting with an H and ending with 2 oxygens, and iode is the root for iodine, as we just said, so HiO2. Finally, copper 2 hydroxide. We don't even need to look up copper since it tells us that the charge is a +2. So copper with hydroxide, since hydroxide is a -1, we know that the formula for this is going to be CuOH2.